So this is from the 2011 Scholarship Physics paper, and this is the first question. No, this is question number 2. It's looking at the gravitational field strength of Earth as you travel outwards from the centre. So with the original centre right here at 0, 0 radius from the centre, that is, and it also shows that there is 0 gravitational field strength. And then once you reach the surface of the Earth, you reach the 10 newtons per kilogram, which is what we'd expect for the gravitational field strength at the surface, what we experience right here now standing on the surface of the Earth. And then the further away that you get from the Earth, it follows an inverse square, or capital R, we'll say, since we've got capital R down here, inverse square gravitational field strength relationship. Now the question A is asking you to explain why you have a 0 gravitational field strength at a 0 radius. And the quick answer, I'll get into a little bit more detailed answer shortly to help you think about this, but the quick answer is that you've got an even mass distribution about you. So to your left and to your right and up and down you have the same amount of mass, and remember, it's the mass of the Earth that causes gravity. If you have an equal amount of mass pulling you to the left, you have an equal amount pulling you to the right, it will cancel out. Another way of looking at it is that a gravitational field is a vector field, has a magnitude and a direction. Okay, so let's just diagram out something to help with that understanding. Imagine this is the Earth, imagine this is you standing in the middle, and do you remember the formula for gravitation, Newton's gravitation formula? Big M, little m over r squared, where r is the radius from, capital M is the mass of the Earth, little m is the mass of you, standing in the centre in this case, and big G is the universal gravitation constant. In the centre you've got the mass to this side, the mass to this side, the mass to this side, the mass to this side. All of your ups and downs, you'll be pulled equally in every direction by the force. So that'll have the effect of cancelling out and creating a null right in the centre, a node, if you like, of 0 mass. Another way to look at it, if that's still not as clear as it could be, is to split the Earth in half and have 2 representative masses. Remember, we take, when we're considering gravitation of gravitational bodies, we usually consider them at a single point in space. So we'd look at those single points right in the centre of each. And if you calculated the Fg using the gravitation formula for each of those, you would have an Fg in this direction and a negative Fg in this direction. And the total sum, so if you're doing the sum of the force due to gravity, it's going to equal 0 because of that. And if that's still not totally clear, you could break this down into a number of representative masses up and down as well, with your mass force due to gravity being applied at each. And if you even wanted, you could break it down into theoretically an infinite number of masses, all split up according to whatever space you have available. Yeah, so I hope that helps. Next question we'll get on to in a tick.